So the first example that we are going to do is the example of the confirmatory factor analysis. So in our earlier discussion, we have done exploratory factor analysis. Now what we are going to do is we are going to do the confirmatory analysis in AMOS. We have these 10 items, these three factors, EMP, task orientation, LEX, and this is the AMOS diagram that we will try to achieve, and we'll see how do we come to it. So we will launch our AMOS, okay, and once you start AMOS, you will get a diagram like, or you will get a window like this, right? So once you start AMOS, everybody, we will get a diagram or image, or I like to call it as a canvas. Okay, so this is our canvas on which we are going to paint, play. Okay, so this is the white piece where we are going to work. Now we want to create a diagram like this. So we want to have EMP having 3 items, okay, task orientation and LEX. How do we do it in AMOS? So there are, on the left hand side, this is the window on which you will have multiple icons, and each icon has its purpose. So you see, if you just hover the cursor on a particular icon, it will tell you what does this stand for. So for example, this square stands for draw observed variables. The oval stands for draw unobserved variables, and then this stands for draw a latent variable or add an indicator to a latent variable. So we will click on this. This is what we want to draw. Okay, so we want to draw our first dimension, which is EMP. Don't draw it very big, because you can zoom in if you want to, but keep it of manageable, reasonable size, because I'm just telling you what we will do in the future. In the future, we are going to add multiple constructs. So your canvas should not be filled with just one construct. Okay, we will need more constructs. So you will see that we have drawn this oval, and just so when you hover the cursor on this oval, it will be highlighted in red color. Click 3 times, 1, 2, and 3. 1, 2, and 3. So there are now 3 items that are there. And then you will see there is this icon called as rotate the indicators of a latent variable. So I click on this and then I rotate. I want to have it like this. Yeah, so this is my first factor with 3 items. Okay, and then I will select all objects. So this hand that you see, it shows select all objects hand. Okay, so I'm going to select. The moment I click, everything is selected here, all of this. So now I will move it, because I can see some of these circles are going out of the canvas. So what do? I say move objects, and I move and I bring it nicely on my canvas, and I deselect everything. I will give this the name. Okay, so I will now remove this bus and I will give it a name. If you double click on this oval, or you can right click and you can go to object properties, the same window will open. So what is the variable name? The variable name is EMP. Okay, or you can write it in small. This is you can change the font size. If you find it to be too big, you can reduce the font size. EMP. Okay, so now let us bring the second dimension, which was task orientation. Okay, so we'll create this again. So I select draw a latent variable or add an indicator to a latent variable. I draw a similar, not a very big oval here, and then 1, 2, 3, 4. 4 times I click, and then I rotate 1, 2, 3. Okay, and I can move and make this. Now you cannot select everything because it will also select EMP. I call it, I find this more like drawing. So you need to make your diagrams look good. Okay. And then we'll give this the name task orientation. And then we bring in our third, which is leading by 3. And then we will rotate. Okay, this is okay, but I can still maybe just move it a little. Okay, and deselect, and give it the name by example font size. Okay, so far, so we have got our 3 factors. Okay, now what we are going to do is let us give this file a name. So we'll save it somewhere. So wherever you are working, so I am working on in this folder. So I will save it, and I will call it as lead first order. Right. So this is my leadership model, first order dimensions. Okay. And I will also read the data file. So this icon here, it says select data file. Okay. So I'm going to add my data file, which is data.sem.sab. And I click open. So the moment you will click, you will see how many sample size. So we have 557 is the N. Okay, it has all identified, and we just click OK. Now, the moment you have read this file, you will see there is a list variables in dataset. Okay, so there is a list of variables that are there in the data set. And when you will open this, you will find a file which has all the data, all the variables that are there in your data file. So now you have to click and drag and drop it here.
You how to open the data again?
The data, okay. So first we read this data. So we have added the data file, okay, wherever we had saved it. Okay, so our data is read. And then you have this list variables in data set, right? So you have this list that opens up, and then you drag and drop your items, TO1, TO2, TO3, TO4, LEX1, LEX2, and LEX3. And you close this. Now you can go to object properties and again reduce the font size. It looks very big. Okay, so you can do it for each one of these. Object properties 14, object properties 14. You can double click also on this and the same window opens up. And then you will, so this is what we have done. And then we will go to plugins. In the top, you will see there is a plugin and you can just say resize observed variables. So the moment you click on this, the variables will be resized. Okay, and everything now, the rectangles will become bigger so that the names can be accommodated within these rectangles. So these are the observed items. These are the three latent factors. And then we also say name unobserved variables. So now you see these are the measurement errors, okay, the circles here. So you click on plugins again and say name unobserved variables. And this again becomes the errors are reported here. Errors are written here. And then that is all. And then you can now what is left in our diagram, if we go and look at our diagram, so we have got these items. What is left is these three double direction arrows. So we are going to create these double direction arrows. So you see double direction, it shows draw covariances. Single arrow says it shows draw paths. So we want to draw covariances. So these are the three paths that we are going to draw. And then there is this wand, magic wand. It is called as the touch-up tool, okay, or it is the beautification tool. So if you click on this, it sort of makes your diagrams look better. Okay, so this is the magic wand to help our models look better. Right, so this is the model that we have specified. This is the CFA model that we have specified, 3 dimensions and their observed variables and their measurement errors. Now what do? We go to analysis properties. So just adjacent to this select data file, you have an analysis properties icon which says, now it shows different things. So estimation, maximum likelihood, okay. This is all default bias. So we are saying covariances are unbiased covariances to be analyzed, maximum likelihood. What is the output we would like to see? We would like to see standardized estimates, sample moments, implied moments. These are all moments, and then we'll report modification indices. Okay, so modification indices are what the software will tell us, okay, in terms of how we can improve. So by default the threshold is 4, because anything less than 4, basically this is nothing but improvement in chi-square. That means if you add a particular path, how much will your chi-square reduce? How much will it reduce? So we are saying report all those paths which if we add to our model, the chi-square will drop at least by 4. Okay, so we'll keep it as default. Okay, and there is this test for normality and outliers, which we should see to actually check for whether there is normality or normality assumptions are violated or not, and whether there are any outliers in the data. Then there is this bootstrap. We will do this when we come to the bootstrap method, when we will talk about in a later discussion, how do we tackle, how do we do analyze data when there is non-normality. So there we will be talking about bootstrap. This is, we'll, these are all general defaults, so we'll not touch that. And then you would see this icon at the on the right side which says calculate estimates. Okay, so we have specified the model, we have given what outputs we wanted in the analysis properties, and then we run calculate estimates. And once you click on this, your model has run and the output is ready. So let us look at this output here. It says number of distinct sample moments. Distinct sample moments is nothing but k plus 1 by 2. Okay, everybody pick up your pen. On your notebooks, we had 10 items, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So what is k plus 1 by 2? It is 10 into 11 divided by 2. So number of distinct sample moments, and that is why this software is called as AMOS, analysis of moments of sample, AMOS. Okay, so the distinct sample moments are 55, k plus 1 by 2, unique entries in your variance covariance matrix. Number of parameters, hash theta, to be specified, to be estimated. So how many factor loadings? 1, 2, 3, 4, 5, 6, 7. 7 factor loadings. How many measurement errors? 10. So 7 plus 10, 17. How many structural errors? Structural paths? 0. How many structural errors? 0. How many covariances? 1, 2, and 3. So 17 plus 3, 20. And how many independent latent factors? 1, 2,
3.
so 20 plus 3, 23. That means the number of parameters to be estimated in the model is 23. So what is the degree of freedom? It is 55 minus 23. K plus 1 by 2 minus hash theta, which is 32. So the degree of freedom of your model is 32. What is the chi-square? It is 118. Degrees of freedom is 32. Probability P is less than 0.001, but we wanted P to be greater than 0.05. So this probability value is actually telling us that we should reject our H naught. That means S and sigma are not the same. The sample covariance matrix. So the model is actually, the result is that the model is not very good. So therefore, we will need to make some changes to this model in order to make it fit well. Analysis summary, let us look at all the outputs and then we will take a break and then we'll come back and carry this forward. So analysis, note this is recursive because it is, there is nothing, no path here anyways. So it is a recursive model. Sample size is 557. Variables, these are the observed, unobserved are these are the exogenous. So number of variables, and you can see it is giving you a detail of this. Parameter summary. parameters. So let us look at this. How many weights? So what are the weights that are being talked about there that are fixed? So what are the fixed weights? All the ones. So 10 for measurement errors and 3 for the factor loadings. So these are the fixed weights. Then what are the unlabeled? Weights are 7. Okay. Covariances are 3 covariances, 13 variances. So 10 for the measurement error variances and 3 for the latent factors, so 13. And that gives us the 23 parameter, right? So this is the parameter estimate. Then we go to normality test, right? So normality is usually, we say that if you were to look at the normality, so there are two things, skew and kurtosis. So skew should be less than 2 and kurtosis should be less than 3. And we are seeing that individual items, the kurtosis is not there. Basically, kurtosis is an indication of peakedness of your distribution. So it sort of shows whether your distribution of this item LEX1, whether it is violating from the shape of a normal curve. So the kurtosis should be less than 3, which is actually supported in all the items. Skew is also less than 2, so the skew is also not there so much. But if you look at the multivariate normality, the multivariate normality is actually telling us that there may be some problems uh, with the multivariate normality. And anyways, let me also tell you here upfront that the moment you talk about a Likert data, okay, Likert data is not a continuous data. Likert scale is not a continuous scale, it is a ordinal scale. So when you talk about this, when you are using Likert scale, most likely the normality assumptions are going to be violated, and therefore we will have to uh, work with techniques which will take care of the non-normality in the data, which we will do later when we talk about bootstrapping. Then we talk about the Mahalanobis distance, which is used to find out outliers. Now, this is the observation number. So we have 557 sample, right? And it shows that, well, the Mahalanobis distance of the first of this 86 from the centroid of the data is 39. This is
But this is
38.
the story in every school
And
college in this country.
and so on, right? So what does this show? It shows that in order to say that there is an outlier, there should be some case which should actually be very far compared to the rest, right? That is when we will say that this case is an outlier. But you see here, the distance is gradually decreasing, 39, 38, 38, 36. There is no case where which is showing. So for example, let's say case number 86, Mahalanobis distance would have been 50. And then the next would have been 38. Now you would see that, well, there is a significant difference. There is quite a big difference between 50 and the next case in the data. So this first case would have been said to be an outlier in the data, which should be removed from the sample. But in this case, we are seeing a very nice gradual decrease. There is no data which is actually showing a very big distance or difference from the others, right? So we say that, well, there is not much of a uh, uh, not much of an outlier that is there. Notes for the model, we have seen this. Then we see the estimates. Okay, so these are the loadings. These are the unstandardized regressions, that is the factor loadings, and then the standardized factor loadings. Then we have the covariances that we asked to report, and these are all significant. So this triple star shows p less than 0.001. The more number of stars means more number of decimal. Correlations, these are the correlations between the factors, and then these are the variances, error variances and the latent factor variances. I will come to modification indices later. Minimization, this is internal. This is what the software is talking about, how it went about optimizing and reaching this thing. And then the model fit summary. So the first one is number of parameters and the chi-square and the degree of freedom. So p-value is less than 0.001. The chi-square by degrees of freedom is also a measure. It is called as relative chi-square. So chi-square by df is called as relative chi-square. Usually we say it should be less than 3. Here it is coming out to be 3.68. GFI is quite okay. It is greater than 0.95. CFI is also greater than 0.95. RMSEA is, well, it is above 0.05, but it is still less than 0.08. So not a very bad model fit if you consider the alternate fit indices, right? And then there are other fit indices, but usually for SEM papers, we look at RMSEA, CFI, GFI, chi-square, DF, and the ratio of chi-square by DF. So, well, the chi-square is telling us, the p-value is telling us that it is not a good fit, but the alternate fit indices are giving us some confidence that the model is okay. So now then this is the execution time, okay. Now we check from the software, is there anything that we can do to improve the fit of the model? And that is what is given from modification indices. So let us take a break here. And what we will do is after the break, we will come back and look at modification indices and how do we improve the fit of our model.